Yes, sir. You can start the session, sir.
Okay. Good afternoon, everyone.
Good afternoon, sir.
Good afternoon, sir.
Okay. Let's start the session with a simple quote. Okay. So there's a quote, we say it as the revision is not going back and fusing around, but going forward into the process of creation. It means the more you revise, it will never be bad for you. It will be more good for you. It will create something good. So I'm starting this session just by thinking that you have revised the last class. So, have you revised the class? Last class? Approximately 4 to 5 days ago, I just took a class. And that much time I was not taking classes because of certain reason. But I'm expecting that you have revised the class. So I'm moving forward. And in the last class, we have discussed about the tautomerism. See, what is tautomerism? It was a special kind of functional isomerism that exists in the dynamic equilibrium. And why it arises? It arises due to the migration of hydrogen atom from the polyvalent atom to the other, and the isomer form are known as tautomers, and the phenomenon is known as tautomerism. So we have discussed, mainly we discuss about the two types, diode system and the triad system. We can also discuss one more type that is called space tautomerism. Okay, space tautomerism we can add on over here. Okay, so let's start basic thing. What you have to remember in tautomerism, there is a equilibrium establishment. Equilibrium is established between two tautomers. It means they are interconvertible. That is, interconvertible forms are present. Second thing, what you have to remember, that there is, you can say there's a difference. There is a difference in position of one atom. In position of one atom, usually, and the thing what we have to study will take as hydrogen atom. So just because we are talking about hydrogen atom, this tautomerism is also known as here, just because we are talking about hydrogen only, and hydrogen is considered as proton. So tautomerism is also known as what? It is also known as phototropism. Prototropism. It means there is a transfer of or migration of hydrogen only. Proto, we represent proton, proton represent hydrogen. So we are talking about hydrogen only, that's why we are saying as proton transport. Okay, that is proton tropism. Yeah, prototropism. Okay. Conditions, what you have to remember, condition number first, what you have to remember, compound must have electronegative atom bonded with multiple bond. Second thing what you have to remember, compound must have one acidic hydrogen. And acidic hydrogen, I'm talking about alpha hydrogen. It means alpha carbon must present and alpha carbon must have one alpha hydrogen. Okay. So these are the certain conditions what you have to remember. This much is okay with everyone? Any doubt in this?
Sir, can you explain once again?
I said in tautomerism, there must be equilibrium between the two tautomers. It means they are interconvertible. If A is forming B, then B can again convert into A. That is called equilibrium establishment. They are interconvertible. Second thing I told you, that there must be a difference in the position of one atom, and usually that atom we considered as hydrogen atom. Hydrogen is also known as proton, so that's why tautomerism is also known as prototropism. Okay, what are the conditions? Condition is that the compound in which the tautomerism is happening, it must contain an electronegative atom which is bonded with a multiple bond. For example, I'm talking about C double bond O or double bond S. Certain condition like this must be there. And second condition, compound must have one acidic hydrogen. It means I'm talking about alpha hydrogen. Okay, so this is the conditions. Now clear?
Yes, sir.
Okay, let's move forward with the type of tautomerism. Type of tautomerism, and the first type I will discuss is diode. Diode means I'm talking about 1-2 system. What is 1-2? I'll tell you. See, for example, I'm taking HC triple bond N. So this is a compound. So here the hydrogen will transfer from here to this particular nitrogen atom. Now the compound formed will be, you'll see, C with a negative charge triple bond N, and nitrogen having positive charge, hydrogen migrated to nitrogen atom. This is cyanide. This is isocyanide. Okay, so generally when there's a migration, between neighboring atom, okay, or if I say the definition of diode, that it involves the oscillation means migration, you can say right now, of hydrogen atom between two polyvalent atom. So you can see now the hydrogen is migrated from the from carbon to the nitrogen atom. So they are interconverted. See, the sign I made is this one. This is called equilibrium sign. But if I'm making this sign, where we use this sign, if you remember, no one remember where I was using that sign. That is called resonance.
Yes, sir.
In resonance, I was using this particular sign. So equilibrium and resonance, what is the difference? Here in tautomerism and resonance, what is the difference? Can anyone tell? What is the difference between the tautomerism and resonance now?
Sir, I think there is no difference between them.
There is no difference in tautomerism and resonance.
So, I mean, resonance, one component to next component, and next component will become the first component. And in the tautomerism also, in the first component, it will change to second component, and after that, it can be changed into second component to first component. Then how can there be a difference?
See, what I want to say, first difference, if I'll say this basic difference, what I can say is, first of all, those forms are not interconvertible. And second thing, there was no migration of atom. The position of atom was fixed in the resonance. Only the bond were rotating. But in this condition, you can see the hydrogen is migrated from one atom to the another atom. Remember, in resonance, there was no migration of the atom. But in tautomerism, there is a migration of atom. And there was no equilibrium established between those two structures. But now we can say there is a resonance, there is an equilibrium. Got my point?
Yes, sir.
So now you can see the difference between resonance and this tautomerism.
Yes.
Okay, second example I'm taking. Okay, second example I'm taking as nitrous acid. What is the formula of nitrous acid? Huh? What is the formula of nitrous acid? Not nitric. Nitric is HNO3. Nitrous, HNO2. HNO2, that is nitrous acid. See, from HO, N have lone pair, double bond O. This is nitrous acid. And if I make the tautomer of nitrous acid, what will happen? Hydrogen, oxygen is bonded with hydrogen atom. Okay, so there is a migration of this hydrogen from this. From this, the hydrogen will migrate from here to this particular nitrogen atom, and now the structure formed will be O N double bond O as it was. Nitrogen will have hydrogen, oxygen will carry negative charge, nitrogen will carry positive charge. Okay, so this is nitro group now. So see, there is a tautomer, there is a movement of hydrogen from the neighboring atom. Oxygen was the neighboring atom. From the neighboring atom, the hydrogen was migrated. So that is called what? Diode system. What we say it as? Diode system. Got my point? So let's start with the triad system. Triad system. So if I talk about triad system, in this triad system, hydrogen oscillates between the three polyvalent atoms. Hydrogen oscillates between three polyvalent atom. It means 1-3 migration. 1-3 migration will take place. Okay, I will show you the basic example. For example, I have X bonded with Y, double bond with Z, and X is having hydrogen atom. And now we have to transfer it. So then a hydrogen, see, this is the first position, this is second position, this is third position. So 1-3 migration, it means the one will migrate to the, what will happen here? Just see. This, no, not to the 2. 1-3 migration, triad system, not to the second one. This hydrogen will migrate to the third one, third atom. And the double bond will shift from this side to this side. So the compound formed will be, the new compound form will be X having a double bond with Y, single bond Z, which is having hydrogen. So you can see there is a replacement. There is a replacement of pi bond and hydrogen atom. Pi bond and hydrogen atom on first and third position. First and third position. I'll show you some example. First, this much you got what I want to say. What I want to convey that hydrogen will transfer from the first to the third atom. Got it? Okay. We'll consider that atom which is having hydrogen. That is the first one, and rest will be in the second one. Okay. So you can see one example. First example, you can see CH having one hydrogen level, CH2 single bond C double bond O single bond R I'm taking. R, it can be CH3, it can be C2H5, it can be C3H7, it can be any of the carbon chain. Okay, now considering the atoms, then we'll go for the migration. 1, then 2, then third. 1-3 migration. 1-3 migration. So the compound form will be, see, this is a ketone, so this is known as keto form. If I'll make the tautomer, it will be CH. Now, see, here will be CH2 double bond, C single bond, O will have H and then R. See, in this condition we have double bond, so we are using ene, and we have OH, so we are using all. So this is called enol form. So this type of tautomerism is known as keto-enol tautomerism. Keto-enol tautomerism. Got it?
Yes, sir.
So let's make one more example. We have to do a certain example so that you can understand more. Okay. For example, we have CS3 C double bond O single bond H. Now tell me, what is the answer? Yes, do the migration. Same type, there's a only one difference in the above example and the below example. I can write it like CH2, one hydrogen above, single bond C, double bond O, single bond H. Okay. Point out the atom. This is first atom, this is second atom, this is third. Okay. Now do the migration. What will happen? CH2, double bond C, O will get the H, and this will be H. So this will be the answer. Got it? Huh? Yes or no? Okay. I'm giving one more example. Now I just want you to tell me the answer. This is keto form. Make the tautomerism. One more example I'm giving. Do the tautomerism. Your voice is not clear. Okay, I'm mentioning the position. First, second, third. Or you can say like first, second, third. 1 to 3 migration. The compound formed will be C. O will have H, the hydrogen from here. It will migrate to the oxygen atom. It will be OH, and double bond will shift to this position. So the compound formed will be this one. So this is enol form. These all are example of keto-enol tautomers. Okay, this one. This one, if I'll go, it will be 1, 2, 3, or 1, 2, 3. So 2 tautomers can be made from this particular example. One will be this OH and one having double bond one having double bond on this position. Another tautomers can be made OH here and double bond will be here. Okay, so the two tautomers can be made over here. Next, one more example. I'm telling you certain examples, but at least revise this because your voice is not clear, Uche. So I cannot hear you properly. So if you're getting my point, then it's well and good. If you're not getting my point, just revise this video again. So this is the compound CH3NO2. Now I have to make a tautomers. So I'll do 1, starting from the 1, then 2, and the third atom. Okay, so now 1 to 3 transfer. 1 to 3 transfer. It will be CH2
NO
N OH. This O will be same. It will be double bond. Okay. One more example I'm taking. CH3 CH2 NO. This is called nitroso. So 1 2 3. 1 2 3. 1 to 3 transfer. Compound form will be CH3 CH double bond and single bond OH. Very good. One more example we are taking. Now the compound form will be, see, this is 1, this is 2, this is a third atom. So the hydrogen will transfer to this particular position, double bond to here. This will be the answer. Okay, last example. CH3 C double bond S single bond H. Okay, tell me the answer.
CH2
CH3
CH2
double bond C
yes, C single bond
bond SH
SH single bond
and H.
H. Very good. So this is the triad system. Got my point? So let's start with the space tautomers. Space tautomers is totally based on the conjugation system. Okay. Certain things what you have to remember is because conjugation is based, conjugation is on alternate positions, and you can say resonance is all occur on the alternate positions. So you'll say the odd position 1 3 5 7 9 sort of this you'll get example. Okay. And one more thing, but you have to, we don't have to don't have to take the hydrogen from the sp2 or sp hybridized. sp2 or sp hybridized carbon hydrogen are not migrated. You have to remember this thing. Okay. And in space tautomerism, why we are saying space tautomerism, just because we don't know from where we have to take the hydrogen. From where we have to take the hydrogen, either from the first position, it can be from the second, it can be from the third, it can be from the fourth, it can be from the eighth, it can be from the ninth. We don't know about from where we have to take the hydrogen atom. So for that particular thing, what you have to do, you have to just see this sp3 hybridized carbon. Okay. So for example, I'm doing CH3 CH, double bond CH, single bond C, double bond O, single bond H. So this is a compound. So in this particular compound, first, see, if I'll do the numbering, first, second, third, fourth, fifth. First, tell me which compound, which of the carbon is sp3 hybridized?
Fifth, sir. Fifth.
Fifth one. Just because single bond is present, the compound found will be CH. So just transfer the hydrogen from here to here and double bond from here to here, just like this. Okay, and this double bond will shift to this particular position. Just to do the conjugation. So it will be CH2, double bond CH, single bond CH, double bond C, single bond OH, single bond H. So this is the tautomer. Got it?
Yes, sir.
So I'm giving you example. Just make the tautomers. I'll give you 4 to 5 minutes. Okay, 4 to 5 minutes I'll give you. You have to make the tautomers. Just draw in your notebook. Just draw it and make tautomers. I'll give you 5 minutes. Think about the sp3, sp2, and then make. First, do this for example. Then we'll have 3 to 4 more examples. Then we'll go for the mechanism of the tautomerisms. Okay. Done. First one. First write the positions. Okay. First we'll see the position. 1, 2, 3, 4, 5, 6, 7, 8, 9. First tell me which is the sp3 hybridized carbon.
Sir, 9, sir. 9.
9 1. Okay, just make the diagram then. Make the tautomers. If you make this, if you have done this thing, then your answer is correct.
Yes, sir.
Okay. Okay. Next one. See, we can make two tautomers of this particular compound. One by the triad also, triad system also. See, you can see 1, 2, 3. Okay, and one you can make like 1, 2, 3, 4, 5 carbon, fifth carbon. Okay, so the two we can make is one will be like this. One from the third by the triad system will be like this one, and another one will be like this one. Okay, this is by the space one, this is by the triad one. Okay, the third one, oh, fourth one. Done. What we will get? In the fourth one, the compound formed is known as what? See the position 1, 2, 3, 4, 5. The fifth carbon is sp2 hybridized, sp3 hybridized. So we'll take hydrogen from here, we'll transfer to here. Okay, then this double bond will transfer here, this double bond will transfer here. Okay, so the compound formed will be OH single single single. What is the name of this compound? What is the name of this compound? Phenol. Yes, fifth one. Do the numbering 1, 2, 3, 4, 5, 6, 7, 8, 9. sp3 carbon is again ninth one. So you'll draw from the ninth only. Double bond, double bond, double bond, double bond. Done this much? Yes,
sir.
got it?
Yes, sir.
Okay. Let's take more example then. Seventh example, we can take this. Okay, draw. Done? So check your answer. Okay, first we'll start 1, then 2, 3, 4, 5, then 6, 7, 8, 9th. Ninth carbon is sp2 sp3 hybridized. So the hydrogen will transfer from ninth here to here. Now the compound formed will be here. It will be we have OH, Now we have one benzene ring here, another benzene ring here. Okay, in this particular case, you can just see sp2 hybridized 1, 2, 3, 4, 5, 6, 7. So now what we have to do? Which one is sp2 hybridized?
I do it. So
Huh?
first,
Which one is sp3 hybridized? Is there any sp3 hybridized carbon?
No, sir. No, sir.
If there is no sp3 hybridized carbon, it means no tautomers. It means no tautomers. Got it?
Yes, sir.
So any doubt in the tautomers? See, let's revise within 5 minutes. From here, first we have done the diet system, HC triple bond N. We have transferred one hydrogen to the neighboring atom, so we are taking it as saying it as diet. Okay. Then we have discussed the nitrous example also. Then the triad system, there was 1-3 transfer, 1-3 oscillation between the 3 polyvalent atoms, and there's replacement of pi bond and the hydrogen atom in the 1/3 position. If I'll say in this particular example, we are forming the keto and the enol form. In the first form, there was 1, 2, 3, and from the first to the third carbon, there was a transfer of proton. So we are saying the keto form is converting to the enol form. So that's why we are considering it as keto-enol tautomerism. Then we have done the keto-enol tautomerism examples. Then we have discussed about the space tautomers, in which we don't know from where we have to take the hydrogen, from where the proton get transferred. Okay, and this totally based upon the conjugation. We'll take the alternate position 1, 3, 5, 7, 9, and so on, just because the conjugation occur on the odd positions. And second thing, you will not take hydrogen from the sp2 or sp hybridized carbon. You always take from the sp3 hybridized carbon. So wherever the sp3 hybridized carbon is present, you will take the hydrogen and the double bond will migrate. When there is no sp3 hybridized carbon, there will be no tautomers. This much I think you got it. If you have any doubt, you can ask me right now, or else I'll move forward in the mechanisms. Clear?
Yes, sir. Yes,
Okay.
sir.
Let's discuss about the mechanism. What is mechanism? When we do the reaction in multiple steps. Okay. So mechanism of tautomers. Mechanism of tautomers are basically classified into two categories. One is acid catalyzed. Another one is base catalyzed. Acid catalyzed means the acid is catalyst. Base catalyzed means the base is catalyst. We are talking about H positive. We are talking about OH negative. Generally. So let's discuss about the base catalyzed reaction. Base catalyzed reactions. I'll give you one examples of both the type. Okay. Of one of triad system, one of the space catalyzed. Okay. First, I'm going with the triad system. See, you can say example is CS3 C double bond O single bond H. Okay. So in the presence of OH negative or H2. So just because OH negative is written here, so it means it's a base catalyzed reaction. So if you'll make the tautomer, we know that the tautomer will form a CH2 double bond C single bond OH single bond H. So this was the tautomer. But how this reaction is actually proceeding, we'll see the process. So in the step one, what will happen? We have the compound CH2 CHC. This is CH3 C double bond O single bond H. And when the OH negative will attack on this particular carbon, OH negative will attack on this particular carbon, the hydrogen will move out from the carbon. It will eliminate out in the form of H2O. OH will take this hydrogen, and the compound form will be CH2 negative charge with the electrons, single bond C, double bond O, single bond H. So this particular compound is found just because the hydrogen is eliminated here. Now we'll make the tautomer, negative charge will migrate here, double bond will migrate here. So the compound formed will be CH2C, here double bond will come here, C, O will have the negative charge and the hydrogen. In the second step, what will happen? See, just because carbon is, oxygen is more electronegative, and if the negative charge is on oxygen, it will be more stable. So in this condition, the stability is less, while in this condition, the stability is more. So now what will happen? Now the CH2 double bond C, O negative and H, they will react with again the water molecule which was eliminated. They will react with the water molecule, and what will happen? This water molecule, it will break and it will get again the hydrogen atom. So it will be CH2 double bond C, O will get the hydrogen H and single bond H, and this OH negative part will be eliminated. So you can see we have in the starting we were getting we gave the OH negative ion, and at last we had the OH negative ion. So the catalyst react in the reaction, but it came out as it was. So this is known as what's the function of the catalyst. So since this reaction is occurring in the presence of catalyst, which is base, so that's what we are saying it as base catalyze. So you got my point in this particular reaction. See, the compound formed is same. You can see CH2 double bond C, single bond OH, single bond H. CH2 double bond C, single bond OH, single bond H. So this is called base catalyzed. Got it?
Yes, sir.
Okay, let's move with the space. For space one, this was earlier it was the triad system. Now let's move with the space system with the base catalyzed. So we have one compound. The compound form will be, we know that the compound form will be 1, 2, or you can say 1, 2, 3. 1, 2, 3, you'll not do the migration. But if you'll write the number 1, 2, 3, 4, 5, if carbon has sp3 hybridized, the compound form will be this one. Okay, so how the mechanism occur? How the mechanism occur? First step will be, see, this is the compound reactant. Okay, we have hydrogen here, 2 hydrogen are present over here. Now OH negative will attack on this particular compound. It will eliminate out water molecule. The compound formed will be, since the hydrogen will move from here and will be eliminated out with the OH negative, the compound formed will be, it will have negative charge in lone pair with a double bond O. Okay, it will form a resonating structure. The compound formed will be, here the resonating structure, negative charge will migrate. Negative charge migrate here, double bond will migrate to this particular position and double bond O. Now again, one more resonating structure will be formed. It will be, the negative charge will migrate here and double bond will migrate here. So it will be O negative. Since O is electronegative, so it is more stable. The compound form will be this one. This is called phenoxide ion. Now this phenoxide ion will react with water molecule. Now this phenoxide ion will react with the water molecule and just take the hydrogen atom to itself, and the OH negative is again eliminated. So the compound formed will be OH. See, phenol is again formed. So you can see how the reaction is processed. There was a tautomerism step in this particular reaction. Got it? some of the resonance you have to take. First, there was elimination of hydrogen. Hydrogen will react with the OH negative. It will eliminate out the water molecule. Now the negative charge is on the para position, which will come in the resonance and make the resonating structure till the oxygen will get the negative charge. When this oxygen will get the negative charge, is quite stable just because oxygen is electronegative. Okay, now the phenoxide, it is known as phenoxide ion. This phenoxide ion will react with a water molecule which was earlier eliminated, and this water molecule will give the hydrogen to this phenoxide ion. It will form phenol, and the OH negative ion will eliminate as it was. So this is called base catalyzed reaction. Got it? Yes or no?
Yes, sir.
Okay, then let's move with the acid catalyzed reactions. Okay, so it's not complicated, same acid catalyzed. So we'll take one triad system, CS3, C double bond, O single bond, CS3. This is known as acetone. If I'll do the tautomer, in the presence of acidic medium, I'll take it H positive. It will make the tautomers. We can do one thing, hydrogen will shift from here to here, double bond to here to here. So it will be CH2 double bond, C single bond, OH single bond, CH3. So let's start with the tautomers. The mechanism of this particular reaction. First step, CH3, C double bond, O single bond, CH3. Oxygen have two lone pair. Okay, so these lone pair, they will attract the hydrogen atom to come towards itself. So the compound form will be CH3, C double bond, O single bond, H single bond, CH3, and oxygen will carry the positive charge with the electrons. Now the double bond will migrate to this position, and the compound formed by the resonance is CH3, C, OH, and here we have CH3, and carbon will get the positive charge. And when the carbon get the positive charge, it is known as carbocation. Okay, what was the second step? Now this carbocation, see, CH2, and I'm taking one hydrogen above it, and then C, OH, and CH3 carrying the positive charge. What will happen now? The H will eliminate out in the form of positive charge, and the compound form will be CH2 double bond C single bond OH single bond CH3. So you can see the reaction is processed with the help of H positive ion. So if the reaction is processed with the help of H positive ion, so it is known as acid catalyzed. Got it?
Yes, sir.
This is again triad system. Last example I'm taking as space catalyzed, the space one. So we have this particular compound in the presence of H positive medium or H2 aqueous medium, we can say. The compound form will be this one, just because we know we have done in this space catalyzed reaction. But how does mechanism occur? Let's look at the mechanism. For in the first step, this compound will react with H positive ion, and it will form double bond O single bond H with the positive. Same negative lone pair will attract the hydrogen atom. Now what will happen? The double bond will migrate to this particular position, to the oxygen atom. The compound formed will be O will have the H positive charge will be on the carbon, and this compound is formed. Now one more resonating structure, positive charge will migrate to the other position. Positive charge migrate from here to here, double bond here to here. The compound formed will be this one. Second step of this particular reaction, the compound at the last form. This is a carbocation just because carbon is having a positive charge. Now the carbocation formed in the above step will react with the will give the hydrogen atoms just because in the starting hydrogen is accepted, so in the last hydrogen must be eliminated, so hydrogen will eliminate from this particular position and the bond formed will be this one. So this is the mechanism. Got my point? Yes or
Sir,
no?
once
Yes.
again.
This one. Okay.
Yes,
See,
sir.
this particular in the starting, the compound will give its lone pair to the hydrogen atom and make a bond. Now, in the second step, the double bond will migrate to the carbon atom. You can say, oh, no, double bond will migrate to the oxygen atom, and carbon will get the positive charge. Since to get the stabilization, we made the resonating structure. The double bond get migrated from this position to this position. Double will migrate from this to this position. Okay, and since the positive charge will migrate from here to here, it will get the positive charge. When the carbon get the positive charge, it is known as carbocation. Now,
Yes.
since we have discussed that if you are taking the hydrogen, you have to
No,
give
sir.
the hydrogen. Yes. Again. Again, pardon what you said.
Double bond, no, sir. OH should have double bond, no, sir.
Why OH should have double bond? This double bond will get the lone in the form of lone pair. No?
Yes, sir.
Yeah, they're in the form of lone pair. I have not mentioned the lone pair here. Okay. So now the hydrogen will eliminate from the para position, and if the H positive will migrate, will move outward, so it will be carry the negative, positive, negative make a bond, and the compound formed will be phenol. So this is the acid catalyzed mechanism of tautomers. Got it?
Yes, sir.
So now the tautomerism is finished. If you have any doubt in any of the isomer in the structural one, in the structural we have discussed chain isomerism, position isomerism, ring isomerism, functional group isomerism, metamerism, and tautomerism. Now I will start with the stereo or the configurational isomerism, and then is geometrical, optical, and conformation. And the chapter will be done. This week I'll complete this particular chapter. So I have 3 more classes this week, Monday, Tuesday, Wednesday. Monday, Tuesday, Wednesday, I'll definitely complete this chapter. And then we'll move for the purification and qualitative, quantitative analysis. Let's discuss with the stereoisomerism. The stereoisomerism. Okay. The stereoisomerism, also known as configurational isomerism. Okay. What exactly happened in the stereoisomerism? You can say the isomerism arises due to different arrangement of atoms or groups in space. Okay, molecules have the same molecular formula but different arrangement of atoms. Okay, and we generally talk about the 3D representation over here. So generally we have 3 types of stereoisomerism. First one is the geometrical, second one is the optical, third one is the conformational. Conformation. We have 3 type of isomerism: geometrical, optical, or conformational. Okay. So let's start first with the geometrical isomerism. Or you can say cis trans isomerism. Okay, so if same group or atom are on same side, then it is known as cis form. If they on different side or diagonally, then they are known as transform. So generally we have to discuss in the double bond over here. Okay, so see, the compound I'm forming is C double bond C, COOH, H, COH, H, and one compound I'm making C double bond O C, COOH here, H here, C double bond OH here, and H here. Now, if you will see on the either side, if the double bond, if the same group are on the same side or in the or near to each other, you can say just close with each other, that condition is known as cis form, while if they are present diagonally, they are known as transform. Okay, so this is the example of this is called malic acid, MALEIC. This is called malic acid. Okay, and this is called fumaric acid. While if you'll see, this is cis form and this is trans form. Why I'm saying this as cis and trans? By the above definition, you can see. By the above definition, you can see both the groups are on the same side. So they are known as cis form. They both are on the diagonal to each other, not on the same side. So they are known as trans form. Clear?
Yes, sir.
I don't think this much is quite tough. Okay.
Yes.
But what you have to remember here, that rotation is restricted. Double bond, there is a restricted rotation, or you can say frozen rotation. Restricted rotation or frozen rotation. Clear? Okay. Let me give you one example. Okay. Can you make U2, 3 diene, like butene. Butene. Example, basic example I'm taking, butene. Which one is cis form? Left or right?
Right.
Right, sir.
This is cis form and this is
Transform.
trans form. Example, you can say. One more example. Let's take last example of geometrical or cis or trans, or only the cis and trans form. C double bond C, single bond COH, single bond COH. This is CH3 here. We have H here. This is called citraconic acid. Okay, and C double bond C. Just take COOH this side, COH this side, CS. Wait, it's not CS3. H this side and CS3 this side. So now, though both the groups are on the different side, now this is called mesaconic acid. Okay, so this is cis form just because COH on the same side. This is trans form. Clear?
Yes, sir.
Okay, then let's talk about E and Z system of nomenclature. E and Z system. Okay. Oh, it's 3-4. We have 1 hour more. Okay, we can complete. I think E and Z we can complete. Optical isomerism we can go for that. Then wedge and dash. No. Tomorrow it will be done, I think. Most probably tomorrow it will be done. Okay, let's discuss about the E and Z. Okay, this particular system is based on the priority. Based on priority. Okay, and it is developed by Can, Ingold, and Prelog. CIP, you can say Can, Ingold, and Prelog. Okay, so the E and Z. E word came from entgegen, which means across or opposite. Some say entgegen, some say entgegen. You can say anything. Just remember, A represent entgegen, which represent across or opposite. While the Z came from the word zusammen, and according to zusammen, it means together. If same priority group, or you can say condition, higher priority on same side. Second condition, higher priority on different side. Two conditions I said. What? Higher priority on the same side and higher priority on the different side. If higher priority on the same side, we will say it as Z form. If same side, we will say at E form. Okay. Okay. This much clear. Then I will tell how we can tell the priority.
Yes, sir.
Yes,
Yes,
sir.
sir.
This much is clear. Okay. What about priority? How will you give the priority? First condition, higher atomic number. Higher atomic atomic number. If higher atomic number, it means higher priority. First condition. Second condition, if isotopes are present. If isotopes are present, then higher mass number. If isotopes are present, then higher number. Okay. If you can say radicals are present. If radicals, or you can say group of atoms, then what you will do? You'll see the atomic number of first atom only. For example, we have Cl, we have SO3H, we have OH, we have NHCH3, we have COOH. So which will get the higher priority. See, Cl atomic number is 17, sulfur atomic number is 16, oxygen atomic number is 8, nitrogen atomic number is 7, carbon atomic number is 6. So 17 will get the highest priority, then 16, then 8, then 7, then 6. Got it?
Yes, sir.
Okay. One more last rule was there. Just give me 1 minute. Okay, just remember these things. These three are sufficient. Okay. If something change will be there, I'll let you know. Although these are sufficient. Okay, let's do the example. Yes. Which one is E and which one is Z? D is deuterium and hydrogen.
First one is E and second one is Z.
First one is
T, sir.
E, sir.
And second one is
Z.
Z.
confirm.
Yes, sir.
Okay. Okay. Now tell me. Which form is this? E or Z?
Z, sir.
E, sir.
Okay. Why E?
Z.
Yeah, Z is correct. C. Cl first. C first. C. Here we have also C. But you see, here we have hydrogen. So these are on the same side and these are on the same side. Higher priority are on the same side. So it is a Z isomer. Okay, one more example I'm giving you. E or Z?
Sir, E only, sir. Z only, sir. Z.
Yeah, it's again Z. First priority, first priority. Okay, atomic number you can see here. Cl second, second. So they are on the same side. So it is again a Z form. Okay. Wait. I'm making one structure. You have to tell me what is the name of this. What is the correct name? I'll give you the option. First option Z 4,6 dimethyl 4-ene-3-one. B option E 4,6 dimethyl 4-ene-3-one. C Z 3,5 dimethyl 4-ene-6-one D E 3,5 dimethyl oct. Okay, I left oct in every example. Oct, 4-ene-6-one. Okay, tell me the answer.
So first option, sir.
Why first option?
Your Me are opposite, sir. That's why Z.
Okay.
O
Huh? I cannot hear you. It's a. Okay, see, it's starting from 1, 2, 3, 4. See on the C, you can see. You'll start. If you'll see this thing, Me and Me. Okay, so they are Z isomer. This was correct. Same priority on the same side. But what about the name? See Z, either there's a possibility, it can be A, it can be C. But what is the name? You need to revise, guys. First option is correct.
Yes,
You need to
sir.
revise. Yeah, it was correct. First option was correct. Okay, let's start with the optical isomerism. Let's start with the optical isomerism. Okay, here we have to discuss about the optical activity. What is optical activity? First, listen this. What is optical activity? It is the ability. It is the ability of substance to rotate the plane of polarized light. In the plane of polarized light. Okay, so we have to discuss about this. So the device we use to measure the rotation, or you can say instrument used to measure a rotation, use to measure rotation is polarimeter. Okay, and optical rotation is expressed in terms of specific rotation, that is alpha. Okay, so let's see first what is optical isomers. First, let's discuss it, then we'll go for the chirality and elements of symmetry and all. Wait, just give me 1 minute. Later configuration we have let's do and leave rotate. Okay, just imagine this. I'm explaining you in a basic way. Okay, there's a simple light in which the poles, their particles are randomly arranged. The particles are randomly arranged, so I'm considering this as simple lights. When this simple light is passed through the prism, we know that there is a diffraction of the light. It will split into 7 colors. But when I arrange one of this prism in the opposite direction and bind it with the help of gypsum, now this prism is known as Nicol prism. Okay, now these two prisms are considered as Nicol prism, and when the same simple light is passed through the Nicol prism, the particles are arranged in the same direction. Now this light is known as plane polarized light, just because they are on the same plane. When I pass this plane polarized light through a solution, when I pass this plane polarized light through a solution, and this solution is known as optically active solution. When I pass this plane polarized light to the optically active solution, this light when passed through it, it either rotate right side or it rotate left side. It either rotate right side, or you can say clockwise rotation, or it can rotate left side. Two possibilities are there. So if it rotates clockwise, we say this compound as dextro-rotatory compound. It is denoted by D form or plus rotation, positive rotation. Okay. If it rotates anti-clockwise, it is known as L form, or you can say L form or minus form. This is a negative rotation. Okay, clockwise, dextro, anti-clockwise is known as levorotatory. See, you can remember like L to levo and L to left. If left side rotation or anti-clockwise rotation, it means levorotatory. Then just do the opposite. Okay. So some definition you have to remember: equimolar mixture of D and L form is known as racemic mixture. It is denoted by DL or plus minus sign. It is denoted by DL or plus minus sign. Okay. And separating DL form process known as resolution. Okay. Why the solution is optically active? We are using here the solution optically active just because solution have optically active because the solution have chiral carbon, or you can say stereogenic center, or you can say asymmetric center. What is chiral carbon? Carbon in which the 4 valencies are occupied by different atoms, in which all four valencies are occupied by different atom. That carbon is known as what? Chiral carbon. So just because of the presence of this chiral carbon, there is a rotation in the light, and we observe this rotation by the help of polarimeter. Okay, so this is called optical isomerism. This much you got? When a simple light is passed through the Nicol prism, it gets converted into the plane polarized light. And when this plane polarized light is passed through the optically active solution, which contain the chiral carbon, in which all the valencies are occupied by different atoms. When this plane polarized light is passed through the optically active solution, the light either turn right side or turn left side. If it turn right side, the compound is known as dextrorotatory. If it turn left side, it is known as levorotatory. Dextrorotatory is denoted by D sign or the plus sign. Levorotatory is denoted by L sign or minus sign. And the equimolar mixture, for example, 50% dextro, 50% levorotation. The mixture is known as what? Racemic mixture. And the net movement will be approximately 0. Okay. And when we separate the DL and form, this is known as resolution. Clear this much?
Yes, sir.
Okay. So, some words you need to remember. For example, you can say carbon, Br, Cl, H, and I. Which type of carbon is there? Which type of carbon is present? Is this
Sure.
carbon is chiral or not?
Chiral,
Chiral.
sir.
It is chiral center. We have a chiral center over here. So if I'll make a mirror image of this particular chiral carbon, you can see carbon Cl, hydrogen this side, Br as it is, hydrogen as it is. So if the two mirror images are present, are these two images superimposed each other? Are these super? Will these two structures superimpose each other? It means cover each other.
Yes,
If I
sir.
take this particular structure and put over this particular structure, will it cover?
Yes, sir.
Not the side ones, sir.
Huh?
I mean, side ones will not cover the atoms, sir.
Hydrogen will not cover the chlorine, and chlorine will not cover the hydrogen atom.
Yeah, sir.
So we cannot say they will superimpose each other. So it means if they are not superimposing each other, it means they are non-superimposable. Am I correct? Yes or no? Are these two non-superimposable or superimposable?
Non-superimposed.
Impossible,
No.
sir.
See, I'm stopping this sharing of a screen for a minute and just look at me. I'll show you some basic. Okay, see, this is my hand, and if I'll cover this particular thing like this, so it is covering. So if it is covering, it means they are superimposable. But if I'll make a mirror image of this, and I'll cover this, and I'll put it like this, so are they covering each other?
No, sir.
No. So if they are not covering each other, just because they are the mirror image of each other, if they are not covering each other, it means they are non-superimposable. And this is called superimposable. This is called non-superimposable. And when I was sharing this screen, just look at it again. Wait. When I was sharing this screen and I made this particular diagram, you can see these two will not cover each other. And when these two will not cover each other, they are considered as non-superimposable. And if they are considered non-superimposable, so we can say one thing: non-superimposable mirror images are formed and they are known as enantiomers. Non-superimposable images are known as what? Enantiomers, or you can say enantiomorph. Enantiomorph. Clear this thing?
Yes, sir.
Yes, sir.
Very good. So let's discuss about the elements of symmetry. This will be, I think, our last topic for today. What is the time? It's 3:28. We have a certain time left. We'll do plane of symmetry, center of symmetry. Okay. And also we'll do the conditions for optical activity. Okay. Wait. Give me 1 minute. Elements of symmetry. See, first thing is plane of symmetry. First element is plane of symmetry. It means when the compound is having a mirror image. Compound is having a mirror image. And if a mirror image is present, it means it cannot rotate PPL, that is plane polarized light, and hence optically inactive. Optically inactive. For example, you can see C, C, OH, OH, COOH, COOH, AH, AH. This is called tartaric acid. So if I'll do one thing, I'll put this is a mirror. Just imagine this is a mirror. So if the first part and second part, are they a mirror image of each other? Yes or no?
Yes, sir.
So if they are a mirror image, it means they are optically inactive here. Okay, so this is called plane. We have mentioned one plane from which the compound is bisected into two equal parts, and from which we can say they are non-superimposable mirror image. They are mirror images. Okay, so they are exactly cut into the two equal half. So this is called plane of symmetry. Okay. Second element is center of symmetry. Second is center of symmetry. Okay, if I'll go with the center of symmetry means it is a point inside a molecule from which, on traveling equal distance in opposite directions, one take equal time. For example, have a molecule so if I'll make a structure, so in this particular structure you can see from here in the mid, from here we can see same time will be for this carbon and for this hydrogen, same for this hydrogen and this carbon, same for this hydrogen and this carbon. So you can see one thing, so there is a particular center in a molecule which is this one. From this center, all of the molecules, all of the side chains or all of the elements which are the member of this ring have equal distance, and from this particular center we can go to any of the atom and will take the same time. That particular center is known as center of symmetry. Okay, got it?
Yes, sir.
Okay, let's talk about the proper axis of symmetry. And in this proper axis of symmetry, we will see the plane from which it will rotate. We will write as Cn. Okay, what is Cn? Here is n time where the collision. For example, I'm telling you C2 axis. C double bond C, one hydrogen this side, one hydrogen this side, one hydrogen this side, and one hydrogen this side. So if I'll go with this particular compound, if I'll put a plane like this or a plane like this, we can rotate the compound. So the C2 C2 axis. It means from wherever if I'll rotate from the horizontal plane, it will come with the same compound. And if I rotate vertically, it will give the same compound. So by adding the plane, there is a same compound formation take place. So that type is called proper axis of symmetry. So here the proper axis of symmetry is C2 axis. Okay, in 360-degree, wherever you can take it. N is the rotation. So this much, just remember this. Let's take asymmetric and dissymmetric compounds. First, chirality and chiral center. I told you what is chiral carbon, which have all the sites occupied by the different atoms. What about chirality? Chirality is the phenomenon, you can say. Okay, a compound which is not superimposable to its mirror image is called chiral, and the compound which is superimposable to its mirror is called achiral. Okay, we can say chirality is basically divided into two categories. One, not superimposable. Another one is superimposable. If non-superimposable, it means it is chiral. If superimposable, it is called achiral carbon. Okay, this much is clear. Okay, last thing I'm doing, and then I'll leave the class. Projection. Projections. What is projection formula? Projection means three-dimensional structures. How you'll make the three-dimensional structure? You have to remember the first thing. First, we will take it as wedge and dash projection. Wedge and dash projection. Okay. So wedge and dash is a three-dimensional structure in 3D shown in 2D. We are showing in 2D, but we are showing what? We are showing a 3D structure. For example, carbon, see these two. For example, I'm taking H on every day. These two are on plane. Okay, these two are on plane. This one is above the plane. This one is below the plane. It means this one is towards the observer and this one is away from the observer. This is sort of representation. You can imagine like that dark line is towards you and the dashed line is away from the you, and these two are on the plane. Just imagine here just imagine 3D. Two things are on the plane, one towards you, that is represented by above one or up one, another one by the down one, which is away from the you. That is the representation. You have to just remember the representation. That's it, nothing more than that. Okay, then next one is dash Fisher projection. Fisher projection. Fisher projection are shown in the vertical form. For example, I'm taking as glyceraldehyde. Glyceraldehyde formula is CH2, CHO. We have one OH here and one OH here. So for showing this particular compound, the two different fission projection can be made. It can be like, see, vertically I'll make it, since we have two carbons, okay, three carbons, sorry. First carbon I'll show as CHO, last carbon I'll show it as CH2OH. While in the mean, the middle carbon is this one. This is the middle carbon, OH and H. And if I'll make a mirror image, OH can be on the left side, H on the right side, CHO above, and CH2OH down. So the two Fisher projection can be made by this particular compound. Got it? How I'm making it? Just open the structure. Just open the structure and make it vertical. That's it. Just open the structure and make it vertical. The compound will be in the Fisher projection. Okay, one more example I'm taking of CH2, CH, single bond COH, single bond CH, single bond NH2. This is a compound known as alanine. It's an amino acid. Okay, so the two Fisher projection I can make of this particular compound. See, first carbon you have to show as it is. Last carbon you have to show as it is. Meanwhile, in the mid compound, one side we have H, another side we have NH2. Just make cross COH, CH2, NH2 on left side, H on right side. So two possibilities are there. Got my point? Yes or no?
Yes, sir.
This is quite easy, I think. Let's, instead of going further, I'm asking some questions from you. Okay. Tomorrow we'll finish this chapter. It's for the short. Tomorrow, day after tomorrow, we'll be done with this chapter. First, I'll ask you some questions now. Okay. Let me see some questions. Wait. Okay, question is, which of the following compound will show the optical activity? Optical activity, which compound it will show? Okay, first is COH. Here we have OH. First, second we have CH3, CH, COH. Third we have CH3, OH, COH. D, we have CH3, Cl, COH. Yes, answer.
So
Yes,
B, sir.
answer.
B, sir.
Okay, why
B, sir.
B?
The four atoms are different, sir, and on the sides, four sides.
Just because if you see, we have similar atom in first, similar atom in the third, similar atom in the fourth. So the compound which have the chiral carbon, which will show the optical activity, the option B is correct.
Yes, sir.
Okay. Another question is, how many possible isomer of butene is A option 3, B option 2, C option 4, D option 5. Yes. Yes, how many isomers are present of butene? See, I gave you the example in the geometrical isomerism. Butene. See, if I'll go for the position isomerism, then only there's a possibility of two isomers. CH3, CH2, CH double bond CH2, or CH3, CH double bond, CH single bond, CH3. So this is the only possibility. So the answer is 2. This was quite easy question. Okay, one more question. Okay, which compound is chiral? Which compound is chiral? First one is butane. Second one is 1-chloro 2-methyl butane. Third compound 2-methyl butane. Fourth compound, 2-methyl propane. Answer. Answer. Make the structure fast. Make the structure fast. Next question I'm writing. Which pair show cis and trans isomer? First option, malic fumaric acid. B, lactic tartaric acid. C, crotonic acrylic acid. And D, malonic succinic acid. Okay, first one, chiral. Which one is chiral?
Sir, is it
First, second, third, fourth.
Sir, I think it is third.
It is?
Third one, sir.
So this is second, this is third, okay? So according to you, this third answer is correct. Okay, anyone else?
Yes, sir. Yes, sir.
How can third be correct? See, butane, it means 4 carbon and 2 methyl is present.
Yes,
CH3, CH, CH, we have CH3, then we have CH3. Okay, and if I'll go over the second one, butane, CH3, okay, 1-chloro 2-methyl, Cl, and we have here CH3. Okay, it's not on second, it's on second position. CH3, first 1-chloro, then 1,2 methyl, and butane, and CH2, then CH3. Yes. Which one? See the chirality. In the fourth compound, you can see one is hydrogen attached, is ethyl. Here we have CH3, here we have CH2Cl. So the second answer will be correct. Okay. Cis trans isomer. Cis trans isomer. Which one is correct?
A, sir. A, sir.
Huh?
A, malic acid and fumaric acid. We have done the example also.
Yes, sir.
Okay. Let me see one more example for you. Okay, question is okay, I'm just telling the question and writing the option. Geometrical isomerism is shown by butane 2-ol, butane, 1-ul, butene, or butene. A, B, C, D. Which will show geometrical isomerism?
So third one.
Third one, very good. Butene. Okay. Question. Geometrical isomerism is not possible in propene, second 3-hexene, C, butene dioic acid, and D, cyclic compound. Yes.
Sir, can you tell me the question once again? I think
Geometrical isomer is not possible in
Sir, option C, sir.
butene dioic acid. Yes, correct. Okay. One more question. 1,2 dichloroethene shows A, geometrical, B, optical, C, ring chain, D, resonance. Yes.
so it's in geometrical isomers.
It's only geometrical. Okay, this question is literally very easy. I'm saying the question, I'm not writing the question. The question is cis and trans 2-butene are conformational isomerism, optical isomers, position isomers, or geometrical isomers.
Sir,
Yes.
cis, sir.
Geometrical.
Geometrical and cis, the before question.
I
you
said,
have.
yes. Cis and trans butene are geometrical. Oh, sorry. First was conformational, second is optical, third is position, and fourth is geometrical. Obviously, geometrical.
Yes, sir.
Butene we have done. Okay. One more example. One more question. Okay, question. Optically active isomers but not mirror images are called. First option enantiomers, second option mesomers, third option tautomers, fourth option diastereomers. Any?
Diastereomers, sir.
Diastereomers. See, diastereomers are those compounds which are optically active, but they are not mirror images of each other. So if they are not mirror images of each other, it means they are known as what? Diastereomers. So just remember this thing, okay? I have not taught you, but I just asked. It's quite easy. Okay, let's wind up. We'll continue the class tomorrow with the remaining topic of this particular chapter. Okay, so this chapter is not that much tough. That's quite easy. Just a conceptual based chapter is there, and we'll complete the chapter maybe tomorrow. Most probably, 90% chances we'll complete the chapter tomorrow, and 10% chances that we'll not complete the chapter tomorrow. So let's revise as much as you can, and we'll see you tomorrow morning 5 a.m. Okay. So complete all the things, whatever I taught you, and in the organic portion, we have only 2 chapters remaining. Main organic. First one is, first chapter remaining is qualitative and quantitative analysis and purification, and then we'll move for the hydrocarbons. Rest, we have completed the general organic chemistry and this isomerism portion. So most probably we'll take one more class for the isomers, then we'll go for the purification method. But before the purification method on Tuesday, I'll ask the question from the past chapter and this chapter. Just because I'm feeling like you guys are not revising for the UPSC. Okay, just revise as much as you can. Okay. Ariana, I'm not audible, guys.
Yes, sir, you are audible, sir.
Okay. Okay, this much is for enough today. This much is enough for the today. I will see you in the next class. Okay. Thank you so much. Have a good day.
Thank you, sir. Yes, students, again we have class tomorrow morning, 5 to 7. Bye, everyone.